Well, hello everyone. Welcome to my channel, YouTube channel on mathematical issues. Today we're going to handle a topic under Ihaji. This topic is known as inner product space. Well, in this topic, inner product space, I would say that everyone to use this topic under Ihaji. Therefore, I call upon you to be able to understand that and be at ease to able to understand this kind of aspect under being algebra 2. I welcome you to all to this kind of a topic. Well, I will start by saying that for you to be able to understand what this topic is, first you must be able to understand what sets are, what an algebra is, so that it will enable you to be able to understand what this kind of problem in algebra 2 is. In a product space, it is an advanced level of the product space. If at all you have to recall what the kind of manipulations that are included in, in vectors, for example, is in dot product, of vectors. I'm talking of if a vector multiplied by a vector, you get a scalar. When you come to cross product, is that when you multiply a vector and a vector, you get a what? A vector. If you multiply a scalar and a vector, you get what? A vector. Well, in this topic, actually, we are going to base our discussions on the illustrations of inner product spaces and giving examples under such. We are also going to deal with adjoints. Adjoints in this perspective, we are talking of the properties that are necessary for any vector space to be known as an inner product space. Thirdly, we are going to talk of definition of inner product space. Today's video we're going to tackle on inner product space only. Then in the subsequent videos we're going to talk, we'll touch on Cauchy-Schwarz inequality and examples and also solving. Then come to triangular inequalities and also linear transformation. But today we talk of inner product space, and under this we talk of definitions, we talk of illustrations and inner product space. And in my previous video, I talk of theoretical explanation of what an inner product space is. And I said that an inner product space, let's take an example of VF as our vector product space. We are saying that if there exists a vector space, let's say VF, right? We are saying that it will be an inner product space is a function that marks the cross product of V into a field of scalars F. Remember, field of scalars is an example of beta, alpha, and whatever. Well, I will give an illustration of what an inner product space is, axioms, and finally I will sum up my explanation on giving definitions of inner product space. Because if you have to define any vector space as inner product space, there are some rules, principles that have to be met with. Well, I will give an illustration of inner product space. Illustration. So I will say if there exists vector space, let's say V of F. Remember, this V of F is a function, right? V of F, let's say f of x and whatever. So I've taken, let's V be any field of vectors space is let's V of F such that the inner product of V This V is a vector space. Okay, is a vector space. It is a function that marks the cross product of V. This is the same V into F. So this F, it is called field of scalars. Field of scalars. Yes. Also, this field of scalars example is let's say alpha and beta. So for this vector space to be called an inner product space, there are some rules, I say axioms, that must be met in order to be called an inner product space. If I have to recall about mathematical computations of vectors, and this mostly serve for those guys who are doing physics on under vectors. If you take a dot product, if you take a vector multiplied by a vector, you're going to get a scalar. Okay, if you take so cross product, if you take a vector multiplied by a vector, you get a vector. So this marks the difference between this dot product and cross product, so that any vector multiplied by any vector you get a scalar, while in cross product we are going to use a vector multiplied by vector, you get a vector, and a vector multiplied by a scalar, you get a vector. So this comes with the linear transformation by extension. Well, if for example I get maybe u in dot product, u multiplied by v, you'll get here a scalar, that is uv. Okay, but this one you get u multiplied by v, I will get here uv, which is a vector. Okay, well, in a product specs, it is an advanced level of a dot product. Well, let's look at the properties of in a product space. These are actually axioms that satisfies any vector to be in a product space. Axiom number one is called complex conjugal. So when I talk about complex conjugal, I will give you an example. Let's say if there exists u and v, okay, which are members of v, okay, right? So you're explaining on complex conjugal, talking of if u comma v, I mean the cross product of u and v, which are members of v. So v here, these are elements of v. Okay, this is a space, so this one are members of v. So when you're talking about the dot product of u and v, it is equivalent to v comma u. Okay, so if you look at this, what is happening here, there's an interchange of vector of this element. Here we began with u, on my right side we have begun with v, so here we put a bar here, so this one means it is a complex conjugate. So in any vector space, for each element you are getting the inner product, so it must satisfy this one. Then secondly, you're talking of non-negative, negativity. Negativity, I mean every element in vector v should not be less than 0. For example, if there exists u in v, okay, you're saying that u, the cross product of u, is equivalent to is greater than or equal to 0. What does that mean? It means if u exists in v, if you get the product of u and u, it must be greater than a 0. And u dot u is equal to 0 if and only if u is equal to 0. So that is negativity. So for any vector space to be called an inner product space, then its element that is within that space, that one of its element taking the product must be greater than 0. And if the product of its element is 0, then u must be equal to 0. Then thirdly, we'll be talking of linearity. So this is property number 3. So if now this one deals with the field of vectors. Now if let's say beta alpha u comma beta v, let's say alpha u plus beta v comma, let's say y. Okay, now we want to talk of linearity. So this is equivalent to, so you're getting this is the cross product. You're getting of you get alpha into bracket u comma v plus v comma y. Sorry, this one is y comma y. Okay, so remember this one is better here. Okay, so this is here is the positive sign, this one is better. Well, if you look at it very keenly, this is the same as u alpha u comma y plus beta v comma y. So as you can see, now this one is an illustration of linearity. But again, this property induces some norm such that if, for example, introduce this norm, if you get u and v is equivalent to, so the cross product of u and v is the same as getting the norm of u dot v. That's it. Okay, so this one is called the norm of this one. Now proceeding to that perspective, if u getting u comma u is equivalent to that one squared. You are talking of u multiplied by u is the same as the norm. This one is the sum of norm squared. And if u let's say that one, the norm of u is equivalent to u getting its square root. So these one are the linearity. Talking of complex conjugate, talking of non-negativity, you're talking of linearity, then talking of these ones. Well, this property induces some norm such that when you take alpha u plus beta v into y is equivalent to
is equivalent to y comma alpha u plus beta v. So this property is known as linearity, no, complex conjugate. But at the same time, this property can be written as this. Okay, talking of alpha. No, we're talking of y. We're talking of alpha u dot y plus this one vy. So this is the second property. This is complex conjugate. This one is linearity, but of the same value. So this condition, we call it sesquilinear, which means that sesquilinear, which means it is 1.5 linear. Therefore, this draws us to definition of what an inner product space is. Well, we will say inner product, let's say V is equivalent to comma that one, such that the product dot product of U, that one, is appropriately in product defined of. Well, if I give you an example of in product space, let's take for an example of real number dimensional space, Rn, such that this one will be maybe x1, x2, x3, x4, and xn. For all x is a member of Rn. So if for example x is a member of R3, so we'll say x is equal to x1, x2, x3, and x3. So because of this, so we have 3 elements, 1, 2, 3. So R. So this one is Rn dimensional space. So if you go ahead and compute the inner product space that are here, let's say y and x are a member of R3, such that x is equal to x1, x2, x3, okay, then y is equal to y1, y2, then y3. So getting the inner product of y and x, let's say x and y, is equal to, you get the summation of this is summation of, let's say n is equal to 1 to n of let's say k xk yk, which is equivalent to y1 x1 plus y2 x2 then y3 x3. Good. So if for example you've been given like x is equal to x x and y are member of R2. This is two-dimensional space, such that x is equal to 3 and -5. Y is equal to -2 and 4. So getting the inner product of x and y is equivalent to getting the summation of n is equal to 1 and n, such that what you do be xk yk, which is equivalent to